Welcome. Today we're exploring a fascinating intersection between chess and computational linguistics. Imagine treating chess games not just as battles of strategy, but as rich sources of data like language itself. In this video we'll see how chess moves can be analyzed using word2vec, a tool originally designed for understanding words and language. By the end you'll see chess in a whole new light, where every move tells a story and patterns emerge from millions of games. Let's dive into this unique blend of chess, data science, and linguistic theory. Word2vec revolutionized how computers understand language by turning words into vectors, mathematical objects that capture meaning based on context. But what if we apply this idea to chess? Just as words gain meaning from their neighbors in a sentence, chess moves gain significance from their position in a game. By treating chess notations as a kind of language, we can use the same tools to uncover hidden patterns and relationship between moves. This approach opens up a new way to analyze and visualize the game. Distributional semantics is the idea that the meaning of a word or a chess move comes from its context. In language, words like week and year are similar because they appear in similar sentences. In chess, moves like pd4 and pd3 often occur in similar positions. By analyzing which moves appear together, we can build a vector space where similar moves cluster together, just as similar words do in language models. This concept is at the heart of using word2vec for chess. Chess games are recorded in a special notation called PGN, where each move is like a word in a sentence. For example, pd4 means a white pawn moves from e2 to e4. By treating each move as a word and the sequence of moves as a sentence, we can feed millions of chess games into word2vec. This allows us to analyze the language of chess and see which moves are related, just as we do with words in natural language processing. Analyze chess with word2vec, researchers use massive datasets, over 5 million games and nearly 840 million moves. Two main types of models are built, one based on sequences of moves and another that includes the full board position as context for each move. By experimenting with different ways to represent the data, we can capture both the flow of the game and the specific situations in which moves occur. This flexibility lets us explore the semantics of chess in depth. Let's break down the types of models used. The first type treats each move as a word and each game as a sentence. The second type goes further, including the full board position as part of the context for each move. There are also specialized models focusing on openings, middle games, endgames, and even whether queens are present. Some models distinguish between moves with and without captures, adding a linguistic twist by treating them like different parts of speech. One of the most exciting features of word2vec is finding quasi-synonyms, moves that are similar in context. For example, the move pd4 is closely related to pd3 and ng1f3, all common opening moves. The model can also identify moves that are out of place, just as it can spot the odd word in a list. This ability to measure similarity helps us understand the structure of chess games and how certain moves relate to each other. Make sense of the high-dimensional data, researchers use TSNE, a tool that projects complex vector spaces onto 2 dimensions. This creates visual maps where similar moves cluster together. For example, opening moves may form one group while endgame moves cluster by piece type. These visualizations reveal the hidden structure of chess, showing how moves naturally group based on their function and context. When we look at the visualizations, we see that opening moves don't form strong clusters. They're all quite similar, reflecting the standard nature of chess openings. In contrast, endgame moves cluster tightly by piece, showing distinct roles for each piece in the final phase. Middle game moves fall somewhere in between with some clustering but more overlap. These patterns help us understand how the meaning of moves changes throughout the game. Some models reveal striking symmetry, especially in games without queens. Moves by black and white mirror each other, highlighting the balanced nature of chess. In other cases, moves by different pieces like bishops on different colored squares form separate clusters reflecting their unique roles. These insights show how the model captures not just the sequence of moves, but also deeper strategic elements of the game. By tagging moves as captures or non-captures, the model can distinguish between aggressive and passive play. Moves to the same square regardless of which piece made them often cluster together. This approach borrows from linguistics, where words are grouped by part of speech. It's a creative way to see how different types of moves function within the broader context of the game. The model even learns about special moves like castling. By analyzing the context, it recognizes that castling involves both the king and the rook and clusters these moves together. This shows that the model isn't just memorizing sequences, it's picking up on the underlying rules and relationships that define chess strategy. By measuring the cosine distance between move vectors, we can quantify how similar or different two moves are. Moves that are nearly identical, like pawns advancing side by side, have high similarity, while moves by different colored pieces are very different. This quantitative approach helps us see which moves are synonyms and which are outliers, offering a new lens for chess analysis. While this approach reveals fascinating patterns, it also has limits. Chess has fewer possible words than language, and the board's constraints limit the diversity of possible moves. Still, the models capture important aspects: the stage of the game, piece color, and typical move destinations. Even without knowing the full position, the sequence of moves alone reveals much about the flow and meaning of a chess game. Summary: treating chess as a language and using word2vec opens up new ways to analyze and visualize the game. While these models may not help you find the best move, they reveal the deep structure and hidden patterns that make chess endlessly fascinating. By understanding the company a move keeps, we gain new appreciation for the complexity and beauty of chess. Thanks for joining us on this journey into the data-driven world of chess.